The death of prompt response discovery. OpenAI's GPT 5.6 Sol is currently managing over 1,000 simultaneous material synthesis simulations within an environment infrastructure called Orchard. This is not a chatbot predicting crystal structures. It is an agentic system using Kubernetes native primitives to execute, monitor, and iterate on physical experiments without a human in the loop. While previous models like GNOME focused on static structural predictions, the Orchard framework provides the Sandbox lifecycle management necessary for models to act as lab operators. The data from the July release shows Sol achieving Pareto improvements in chemistry and life science workflows, suggesting the bottleneck has shifted from model intelligence to environment scale. This is the first time we are seeing a model move from text output to direct management of the experimental lifecycle. The mechanics of the Orchard Sandbox. Orchard is not a fine-tune or a new reasoning method. It is a specialized infrastructure layer acquired during the Cirrus Labs merger. It functions as a thin service that manages agent sandboxes, allowing a model to spin up a virtual lab environment, execute code to control hardware, and process real-world feedback loops. The system uses what the paper calls prospective credit assignment, which trains the agent to anticipate how a specific chemical mixture today affects a synthesis outcome 10 steps later. Instead of a single inference call, Orchard facilitates a continuous trajectory of actions where the model self-corrects based on sensor data. This architecture explains why the July 9th benchmarks show such a massive jump in long-horizon task completion compared to the older GPT 5.5 series. Why the chemistry benchmarks shifted. The real story is in the MedChem Bench and GeneBench Pro results, where GPT 5.6 Sol outperformed prior models by 30% in error recovery. Skeptics point out that these benchmarks are often saturated, but the Orchard integration allows for testing in non-deterministic environments where things actually break. In these tests, the model isn't just reciting chemical properties, it is diagnosing why a specific material synthesis failed and rewriting the protocol in real time. Think of it as the difference between reading a cookbook and managing a professional kitchen. The model's ability to handle the messy, reactive nature of physical science proves that its internal representation of physics is significantly more robust than the probabilistic word matching we saw in earlier architectures. This leads directly to the question of industrial scale. The signal under the noise. The shift from the Orchard agentic framework to GPT 5.6 Sol's autonomous science capability signals the end of AI as a creative assistant and its birth as an industrial utility. By combining the Kubernetes environment management seen in the Orchard infrastructure with the long-horizon reasoning of the Sol model, OpenAI has effectively industrialized the scientific method. For builders and researchers, the implication is clear. The value is no longer in the weights of the model alone, but in the quality of the closed-loop environments they inhabit. We are moving toward a reality where materials are discovered and verified in the time it used to take to write a research proposal. This trajectory suggests that by the end of 2026, the primary metric for AI success will not be benchmark scores, but the volume of physical patent filings generated by autonomous systems. Watch for the next update on the Stargate Data Center, which is designed specifically to host these high-density experimental loops. Subscribe for more.